Hello everyone, Mr. Fawcett here, and we are back for another AP Calculus lesson. Today we're going to talk about how to differentiate inverse functions. So you've likely looked at these inverse function in Algebra 1, Algebra 2, and Pre-Calculus. Today we're going to review some of those relationships between original functions and their inverses, and then we're also going to talk about how to find the derivatives of inverse functions and hopefully provide you with the most efficient method to finding these derivatives. So first thing I want you to do is think about any relationships that you know about functions and their inverses. And just jot them down right here, pause the video, and then we'll see if these thoughts that you had end up being true or whether they were some misconception that you may have had from previous classes. All right, so let's jump right in. So if f of x and f inverse of x, so the notation for inverse functions is just that little -1. It looks like an exponent, but we don't say f to the -1. We say f inverse of x. So if f of x and f inverse of x are inverses, then the domain of f of x is equal to the range of f inverse and vice versa. And the range of f of x is equal to the domain of f inverse. So there's two types of representations we'll talk about. One is the graphical. So if we have a function and its inverse, well, if you only know one of the functions, right? So let's say we only know what f of x is, and let's say we know that f of x looks something like, we'll just do something easy. Something like that. Well, to find the inverse of f of x, you would reflect f of x over the line y equals x. So you reflect it over the line y equals x, and you would get something that looks like this, right? So these two functions, because you can reflect one onto the other over the line y equals x, they would be inverses of each other. And we're not going to talk too much about how to graph inverse functions. We're not going to be doing a lot of graphing of original or inverse functions in a calculus class, but it is good to have a more complete picture of the relationships between the original function and its inverse. Now, if we jump to the analytical representation, this is something we're going to focus on a bit more in this class. And actually, what we put here in this box is very important when it comes to being able to derive the formula for the derivative of an inverse function. So this relationship right here, if f inverse is the inverse function of f of x, then two things are true. F of f inverse of x is equal to x, and f inverse of f of x is also equal to x. So again, just a quick example here, what this would look like would be if I had something like f of f inverse of 2, that's always going to be equal to 2. And then down here, if I had f inverse of f of -5, that's going to be equal to -5. So again, these two relationships right here, this one and this one, both of them would be important to know. Okay. All right, let's go down and put these things to use in some practice problems. Put these ideas to use. So we're not actually getting into the calculus yet. We're just going to practice some of these relationships between functions and their inverses. So they give you a table here. It gives you the input, the x, and then it gives you two outputs, f of x and g of x. And again, I'd encourage you to pause the video, see if you can fill in these 6 boxes below. We're not going to go through all of them, but we will touch on about half of them. So try to work through them, and then you can see how you did by coming back to the video. Okay, so let's look at box number 1. We'll just call that one number 1. It says complete the table of values below. So for x, and we're talking about f inverse of x. So we should be able to come up with 2 inputs for f inverse and 2 outputs for f inverse. And we have to think about the relationship, right, that the domain of f of x is equal to the range of f inverse, and vice versa. So what this is saying is that if we look at these 2 columns right here, these also mean something else. So we can also label these as such. If we switch the domain and the range of f of x, that gives us the domain and the range of f inverse, which means that my 2 x values are going to be 3 and 2, and my 2 f inverse values are going to be -2 and 1. Same can be said for g of x, right? If I'm going to erase what I have here, but you can keep it on your paper. If I don't focus on this middle column at all, because I don't need to worry about f of x for this box, well, if I switch the domain and the range for g of x, I get g inverse and x. So again, this gives me a new domain and range for my inverse. So I get 1 and -2, and then my g inverse of x values become -2 and 1. So sometimes it helps me to just relabel the columns with my new domain and range when I'm talking about the inverse of a function that's given. Okay, let's go and do this one down here, the first one in the second row. So it says find the value of f inverse of f of 1. So we actually shouldn't have to look at any boxes here, shouldn't have to do any work if we remember one of the relationships from up above. And I said this is going to be important as we proceed into further problems. And that relationship, one of the relationships was, if we take the inverse of the original function, that is always going to equal whatever that input is. So here, our input is 1, so this is going to be equal to 1. And you could actually look at the table and just check this real quick, right? So let me relabel. Actually, we already have our 2 boxes labeled. So f of 1 is 2. Let me get my pen out. F of 1 is 2. All right, that's f of 1. So if I substitute in 2, then I'd have f inverse of 2, and I'd come over to this table. My f inverse of 2 is 1. So again, you can check your work there, but you can also just know the answer immediately if we understand that relationship between the function and its inverse. Okay, let's do one more. Let's do one where we cross between the different functions. So let's come up here to the third box in the first row. It says find the value of f of g inverse of -2. So this time, because the functions are different, we can't just say our answer is -2. It's not going to work that way. It may be a coincidence that the answer is -2, but we can't know for sure. So when we're working with composite functions, we always evaluate the inside function first, or the innermost function, because you could have a composite function with 3 functions like we have down here, but we just always do the innermost function first. So g of g inverse of -2, not sure where I got -1 from, g inverse of -2, well, we're going to be looking at this box right here, g inverse of negative 2 is equal to 1. So this simplifies to f of 1. I come up here, f of 1 is equal to 2. F of 1 is equal to 2. So again, when you're evaluating a composite function, just evaluate the innermost function first and eventually work your way out to the outermost function. All right, since the other two boxes are fairly similar to what we just did, I'll let you continue those on your own, and if you have questions, you can always ask me. Now we're going to get into what the derivative of an inverse function looks like. So let's erase this, and let's look down here. All right, so the question that's going to lead us into our discussion of derivatives of inverse functions is this. If I give you the original function, so they give you an f of x here, would it be possible for you to find the derivative of the inverse function? So f inverse, that derivative. Well, maybe you've learned some things in your previous math classes that could help you answer this question. I'm going to encourage you to pause the video, take some time to think through this, struggle a little bit if it's not immediately apparent how to do this, and then come back and we'll have a discussion. Okay, so my guess is that you thought, well, if I need to find the derivative of the inverse function, I might need to find the actual inverse function first, right? Whenever we've done a derivative, we've always known what the original function is, unless we're given a derivative in the form of a graph or a table. But if they ask us to take a derivative, we need to start with the original function. So is there a way to find the inverse function here? So let's do some work off to the side to find the inverse. Well, based on what you've learned in previous math classes, you were probably taught to switch the x's and the y's and then solve for y. So this function doesn't have a y, but we can replace the f of x with y, just to write it in a different form. And then if I switch my x's and my y's, I get x is equal to y cubed plus x plus 2. Sorry, plus y plus 2. Goodness. Y cubed plus y plus 2. Now, you could use this equation right here to find values of the inverse function, right? You could, it has an x and a y, so you could, come up with different points on that inverse function. But we want to be able to write it as f inverse of x is equal to something. And to do that, we need to get the y by itself, just like we had up here. So again, next step would be to try to get the y by itself. So maybe you played around with this. Maybe you were trying to think hard about how could I combine those two y terms? How could I maybe get rid of the cube? And you probably were unable to do it, right? Because it seems virtually impossible to do this by hand. So sometimes, right, it's not easy to find the inverse function using this method. Now, for linear functions, for some quadratic functions and cubic functions that only have one y term, right, it may be straightforward how to find the inverse function. But when there's multiple y terms and you can't factor, you can't do other things, we just kind of get stuck. So we have to think back to the original question. The original question wasn't to find the inverse function. It was to find the derivative of the inverse function. So maybe there's a way to forego this middle process. Maybe we don't, oops, I meant to use my pen. There we go. So maybe there's a way to forego this middle process. Maybe we don't actually need to find the actual inverse function to find the derivative, because that method was clearly not getting us anywhere. So to finish off the part one of this video, we're going to talk about exactly how to do that. How can we just go from the original function to the derivative of the inverse without actually finding what the actual inverse function is? To do that, we are going to start with this important relationship up here, that f of f inverse of x is equal to x. So we start with something that's true. We know that this is true. Now what we're going to do is we're going to take the derivative of both sides. So I'm going to, let me write this up here for us. I'm going to do this over here just because I have the most space. So I'm going to do d dx of f inverse of x is equal to the derivative, so d dx of x. Well, the derivative of my right side is pretty straightforward, right? That has to be 1. Derivative of x is 1. Derivative of my left-hand side is a little bit more difficult. It implies a chain rule because we have a composite function. So if we remember the chain rule, we do the derivative of the outside. So we get f prime of f inverse. Oops, that's too large of a 1 there. Of f inverse of x times the derivative of the inside, so the derivative of f inverse. And the way we're going to write this, it's going to look a little funny. We're going to put the little derivative marking, that little tick mark, on the outside, just because we don't want to confuse it with the -1 that is used to denote that this function is an inverse. Okay, so all we did here is apply the chain rule on the left-hand side. If you're unsure of what just happened, pause the video, rewind it, and think about how the chain rule works and how we got from line 1 to line 2. Now, think about our goal. Our goal is to find the derivative of the inverse function. So we need to get this term by itself, right? Because then we'll have something that's equal to the derivative of an inverse function. Well, to do that, we are going to divide everything by this other term, f prime of f inverse. And we'll just say we're dividing everything, so I don't have to write it twice. So we end up getting the derivative of f inverse is equal to 1 over f prime of f inverse. And this is going to be our formula for the derivative of an inverse function. Now, this looks pretty complicated. There's a lot of original function, inverse function notation going on here. But the more we work with it, the more it'll make sense. And the nice thing about this is that if we ever forget what this formula is down here, right, I would encourage you to memorize it. The more you work with it, you'll memorize it. But even if you don't memorize it, you can figure out what it is, right? As long as you remember this relationship up here. If you remember this one thing about functions and their inverses, well, you can just take the derivative of both sides to end up figuring out what the derivative of an inverse function is, right? And I'll tell you, there's times when I haven't worked with derivatives of inverse functions in a while. I just have to go derive it myself, right? But I don't have to look it up because I know what that original relationship is. Okay, so again, we just followed these steps here. I just did it off to the side. So all of those questions led us to the pink box on the left. Now, I believe the last question says, where would the derivative, oh, you know what? I forgot one little tick mark here, guys. We need that derivative notation. So we're talking about the derivative of f inverse. And I believe the last question says, where is the derivative of f inverse or the derivative of inverse functions undefined? Well, the derivative of f inverse is undefined let's just get rid of that whole thing and try again. It's undefined when, and I'd pause the video and see if you could fill in this blank. When will the derivative of f inverse be undefined? And it's going to be when that denominator on the right-hand side is equal to 0, right? Because we can't divide something by 0. So this is when f prime of f inverse is equal to 0. So if that quantity is equal to 0, our derivative is going to be undefined. All right, we're going to pause there for part 1. We're just over 20 minutes, and when we come back for part 2, we'll actually look at applying this formula to actually finding some derivatives. But the one takeaway from part 1 should be this relationship up here. Because if you know this relationship, you can always derive the formula for the derivative of an inverse function. And as we can see from this side right here, it is only about 2 or 3 steps. All right, enjoy the rest of your day. I look forward to seeing you for part 2.